so let's go for it here. Still in chapter 2. And last time we covered this called the library of functions. Is that right? Covered all the different types of functions we have studied from algebra. So now what happens in 2.7 is we start manipulating it. So yeah, we have this sort of parent function called the square root function. That's great. We've got to be able to move it around. What happens if it's going to double? What happens if it goes half of that? Or what happens if the parabola goes up faster? How do we compensate for all those things? So that is what we call transformations. And we have transformations different ways. We have a vertical or a horizontal shift. And by shift, what I mean is individual points just going up. So the whole graph, every single point goes up, or it goes off, or it goes bottom, or it goes to the right or to the left. But the whole graph shifts. Reflections, if you think back to symmetry, that's what reflections are. We're going to reflect it across the y-axis or across the x-axis. All right, then we have something called stretching or compression. Stretching is now, you can say, it's going to go up faster. So what happens if you go faster? What's the equation for it? And then compressions as well. All right, so let's go for it. All right, transformations. It is basically a new function formed by manipulating we call it a parent function. And so a square root is a parent function. What happens if you have 2 square root of x? Or sorry, square root of x is a parent function. What happens if you have 2 square root of x? That's going to stretch it up twice here. Just a quick example here. And we're going to get to a more like a general formula at the end of 2.7. But let's go from specific and we'll get to generic formula. That's what we want to do. So, and I think you guys know some of these from at least the easy stuff, you know, from algebra. So you have a square root of, absolute value of x. You have the absolute value of x, and then you got an extra little 2 at the end. What does that little 2 do? Kind of tells you here. It's going to do a vertical shift on you. The positive 2 goes up. Because you have the minus 3, it's going to go down. The relationship here. Notice this little number at the end, really what it's doing is because it's outside of the function itself, once you do the function, absolute value in this case, you're just going to add 2 to it. Or you're going to subtract 3. So it doesn't affect the function as much as it affects just the last final thing you do to it. So the graph of it, there it is. The square absolute value of x is here. Adding 2 moves it up. Subtracting 3 moves it down. All right. Our function here. All right, and if you want to have, let's see, your book open to, maybe a good page to have it open to is 234. Because page 234 has all the different types of functions we've covered from 2.6, sort of on one single page. And there's 12 of them that we've covered so far. All right, go slow on the first one here, and then we'll sort of get going faster and faster here. So x cubed, again, going back to 234, or memorizing it yourself here, you should know what x cubed looks like. Then you have x cubed plus 1, x cubed minus 2. So let's go to graphing here. So graphing x cubed, again, using page 234 if need be. So if you say cube 0, it's still 0. If you cube 1, it's still 1. If you cube a 2, it jumps to 8. So, all right, if you cube a negative 1, gets you to negative 1. Cube negative 2, again, gets you to negative 8. And then at this point, you know what the function looks like. Kind of goes like this. The arrow's going both directions. Good there so far? All right, now let's start manipulating in here. So what is x cubed plus 1 going to be? It's these individual points. We're just going to move them up one notch. That's it. So this guy moves up one notch. This guy's going to move up one notch. This one's going to be a -1, 0. This one's going to be a -2, -7. So individual points get moved up. And then put it together. Now, of course, got to do the trivia question here. As the graphs go up and up and up, are they getting closer and closer to each other?
Yeah.
Love it when it's kind of like, there's some stuff in theoretical mathematics, it's called counterintuitive, which you think it's this, but it's really not. We're good? So it's right here. Are the two graphs getting closer and closer together? No, they are not. They are always, always, always 1 unit apart. These guys are always 1 unit apart from each other. Because whenever we talk about getting closer to each other, we're talking about a single x and seeing what's the difference. In this case, the difference is 1 unit always. Kind of like railroad tracks, right? You look at a railroad track, you think, oh wow, look, they're going to get closer and closer together. No, they're not. It's railroad tracks. They're always the same distance apart. Okay, going down here. So x cubed minus 2, which means we take the first line that we made and we're going to go down 2 units each time and every time. And we keep on doing that on the other side as well. And then there's my third graph right underneath, now 2 units away each time. The absolute value graph, that was a little bit better one to look at, because then you can really see that they're always certain units apart from each other. All right, and I think the first 3 that we're going to do, that's stuff you've seen in from algebra. So this one, what we label this as, the vertical shift. It's labeled as D, and because there is going to be a reason for it. It's whatever numbers at the back of the function. Notice you got the function here. This is my function, whatever it is, square root or absolute value or whatever. The D value is at the end. So if it's positive, it goes up. If it's negative, it goes down. Okay, let's try another one here. Or let's try something different, actually. All right, for our practice problem, it's x cubed. And then we have x minus 1 being cubed, x plus 2 being cubed. And again, this one is something called counterintuitive. The parent function is x cubed. If you say x minus 1, what we're really going to do, this one's actually going to shift to the right. Because you're asking yourself, this is, what's going to cause this to be a 0? 1, right? If I plug in a 1 for x, 1 minus 1 will cause that 0 to happen here. So let's go for it. Let's graph x cubed. We'll graph x minus 1 cubed. So x cubed, as we graphed on the previous problem already, looks like this. All right, now we're trying to graph, actually I should say put y, g of x, sorry. Here's my original function, x cubed. G of x, the next one is going to be x minus 1 cubed. So as I plug a 1 into there, you kind of notice what's going to happen here. 1 minus 1 is a 0. 0 cubed is going to be a 0 right here. So now plugging in a positive 1 gets me that 0 value. Plugging in a positive 2, 2 minus 1 is 1. 1 cubed gets you right over here. So with the x minus 1 into the function, you have a shift to the right 1 unit, and then based upon what we just figured out here, we can put the other ones in. So this one here is going to go here, -2, -8. Now it's going to go to -1, -8. All right, quick show of hands. How many remember this from algebra? I remember this from algebra. All right, a whole 4 of you. All right. Rest, or just sleeping? Okay, are we good there so far? So the number inside, if it's a negative, it shifts it off to the right. All right, next one. I think it's H. Let's see, H. Yep, H of X. The other one was X plus 2 to the third. So again, from this parent function that we graphed, what are we going to do? Left 2 units, right? You're thinking what's going to cause that 0 inside there here. So we're going to take that 0, 0 marker, move it over. The next one, 1, 2. That should be right here. So 1, negative 1. Negative 1, 1 should be the next one. Move this over, 1, 2 should be 0, 8. And the rest as well gets moved over. Put a curve through all that. And some arrows at the end. This one shows a little better of how they're just exactly certain units apart from each other. Okay, so what conclusion can we draw? It's in the textbook here. We're saying this, y is equal to f of x minus c. Notice the c is now inside the function. And notice there's a minus sign. That minus sign is really saying the direction is going to be changed. So if you see x minus 7, you know you're going to go 7 units to the right. We're going to put it all together at the end here. We're going to have one big generic function here. All right, so now let's put both of these together real quick. So practice problem number 3. All yours now. You have a square root of x is the parent function, looks like. You have a minus 2 that's inside the function. You got a plus 3 outside the function. I'll give you guys a few minutes here. Try it yourself. All right, so let's go for it here. We have, first of all, we're going to at least graph this one. This is the parent function, the square root of x. You should know what that looks like. Bless you. And what we usually do is we just put in dots. We don't really graph the function itself, because why have 3 graphs when you really want to do 1 graph? So the question is, for square root of x, where are the important points for the square root of x? Well, I think 0, 0. Is that an important point? Square root of 0, 0? So think about perfect squares here. 4 would be a perfect square of 2. So 1, 1. Sorry, I forgot about that one here. Then we have 4, 2. How about that? We have, let's see, 9. Square root of 9 is 3. So there's my parent function. It goes off like this. Something we talked about last time in 2.5 called the parent functions. Then what we have, it doesn't matter which way you go. You can add 3 to it. You can do the horizontal shift or the vertical shift. Doesn't matter which way. So let's go for it here. I'm going to, in fact, let's do it at the same time here. That's 0, 0. It's going to shift 2 to the right, 3 up. Or you can go 3 up, 2 to the right, doesn't matter. From 1, 1, again, we're going to go 1, 2, 1, 2, 3. That shifts up to about right here. So notice we're just moving individual points. 1, 2, 1, 2, 3. And this one's off the chart already. That's okay if it's just a little bit off the chart here. How about 1, 2, 1, 2, 3? How about right into here? And how about a graph that goes like this with the arrow? Are we good? Sure. Honesty question. Raise your hand if you read 2.7, or at least looked at 2.7 before coming to class today. 1, 2, 3, 4, 5. Whew, all right, all 5 of you. Cool. Thanks, dude. Math class, have to read ahead. Okay, let's go on. So those were vertical shift, horizontal shifts. I think you've covered those in algebra. Those are the first. Then we have something called the reflection. We have 2 different types of reflection, something across the x-axis, then we have another one called the y-axis. Okay, so what happens here is notice this little negative, that's outside the function. So notice it's y equals negative of my function itself. If you see a negative in front of the function, you got yourself a reflection across the x-axis. What does that look like? And it has a graph. There it is. The blue graph here is the original. And all we do is we just change the sign on my y value, bring it down to the bottom. Okay. More confusing? The y. When do we know we have a y-axis symmetry, or we can actually reflect it across the y-axis? Is if you have a negative that's actually inside the function. Again, we'll look at some examples here in a bit. If you have a multiplier of a negative inside the function itself, there's that type of reflection. Okay. Good there. Geometrically, what does that look like? It kind of looks like this. If you have a function over here somewhere, we're just going to move it across the y-axis, put it right over here. So now the sign of your x value changes. All right, let's take a look at a practice problem here. All right, it says explain how to graph it. That's okay, just graph it here. So you have y is equal to, you got your little negative right here. Got yourself x minus 1 being squared, and then you got yourself a plus 2. Again, parent function is x squared. Let's see how we can manipulate this across. And again, I'm kind of just doing one example per each. We're going to keep on going. Okay, so first and foremost, we probably should graph this guy by dots, just by individual points. What does x squared look like, individual points? And then we're going to try to manipulate it based upon these 3 things here. All right, again, that's my original function, just so I don't forget it here. I am going to graph x squared as my parent function. That's what I'm going to start with for my library of functions. So x squared, 0, 0, 1, 1, 2, 4, right? 3, 9. Then it's symmetric along the other side. Do we need to do all those points? No, you don't. But you still just need to have at least for x squared, probably at least 3 points, maybe 5 of those points. All right, take as many steps as you like. What I'm going to do first, I'm going to do the negative first. So now I'm going to, by individual points, let's graph negative x squared. All right, let's see. A negative outside the function means reflection about the x-axis. So if you can kind of see that little green dot right over here, 0, 0 just got mapped onto 0, 0. No changes there. And then I start moving things down here. So 1, 1 now became 1, negative 1. 2, 4. How about 2, negative 4? 3, 9. 3, negative 9. And so on and so forth. All right, still notice I'm not connecting them yet. No point in connecting them. Take those green dots now. Now we can work with. We got this so far. Now let's put in the final things here. That little -2, we're going to move off to the right 1 unit. And this one, it says we're going to move up 2 units. So let's take this little 0, 0 marker here. Let's go 1. And we'll go 1, 2. So that 0, 0 now became 1, 2. Right there, where that red dot is right now. So at this point, we're just moving individual points. All right, whichever one else we want to use here, let's move this guy here. So this is going to be 1 to the right, 2 up. This one's going to be 1 to the right, 2 up. 1 to the right, 2 up. Now we go to this point here, so 1 to the right, 2 up. 1, 1, 2. 1, 1, 2. All right, we've transformed. Just to get the sound effect, so we do. Okay, putting it in, we're good to go. There it is. We have graphed negative of x minus 1 squared plus 2. Got a few people still writing it out. Go for it. Check my time so we're on schedule. Cool. All right. Where's the stuff used at? Maybe just one single use for it is, remember when distance can't be negative. There's no such thing as that. Distance always has to be a positive value here. So this is maybe one use. We take our function, in this case x minus 1 squared minus 4, and what we do is we just take the absolute value of the function itself. And so notice the blue graph, the original graph here, comes back down here. So if we're saying, okay, hold on, we're going to think of this as time, or we're going to think of this as distance. Most likely distance in this case. So you can't have distance to go underneath itself, or not underneath. So what we do is we just say, hey, we're going to take the absolute value, or we're going to reflect anything that's underneath the x-axis, we're going to reflect it to the above the x-axis. So in this case, the vertex pointer here, -1, -4, gets bumped up to -1, +4, and notice, hey, doesn't that look like a bounce of a ball, doesn't it? Boink. So let's go for it here. Let's do one simple one for us. All right, you got 2x minus 4. Can you sketch that graph first? And after sketching the graph, can you take the absolute value of the graph? Or in a sense, you're reflecting anything below the x-axis to above the x-axis. All right, give you guys half a minute here to start with. All right, let me start it as well. So if I'm going to graph 2x minus 4, isn't that sort of what mx plus b, is that right? So my y-intercept is -4, my slope is 2. I think I can do that. So start off -4, I'm going to go 1, 2 up, 1 over to the right. I could do that again, 1, 2 up, 1 over to the right. At this point, I can probably make a little graph, right? It's just a straight line, no problem there. All right, but again, what I really want to do is make the absolute value of this here. So whatever dots I have here, again, it's really just a reflection. But it's a reflection just when it goes under the x-axis. So this little 1, -2, let's bring it up to 1, +2, and maybe this 0, -4, bring it up to a 0, +4 at this point. And so I'm going to just kind of place the next one. I should make another graph over here. Really, what should I be doing? But I'm going to just kind of put it like that, one graph on top of another one. Just make that second one maybe a little darker, then you know where that one is. All right, good there. That should be a somewhat easy one here just because it's a linear function. All right, now we move on to some other stuff here, something called vertical compression and vertical stretch. Again, this one you've probably seen in algebra still. Then we get to horizontal compression stretch. That's one you probably haven't seen in algebra. So let's go for it here. So what happens if you have a number that's actually in front of the function? So notice our parent function is the absolute value of x. What we have is we have 2 of that, or 2 times that, and then you also have 1/2 times the absolute value. Just as an example, I'm not going to do this one. What's really happening between the functions here? Notice between f of x and g of x is just going up twice as fast. So maybe a graph would be easier to see. So the original function is this blue one right here. There's your absolute value. So if you go 1 over to the right, you're going to go 1 up. With this little 2 in front now, you're going to go 1 over to the right, and you're going to go now 2 up. So it's going to go up twice as fast, or it's going to actually be going down twice as fast. For this one, the 1/2, the 1 over to the right, you're only going to go up 1/2. So if it's bigger than 1, we have ourselves a vertical stretch. It's stretching out vertically, going up faster or going down faster. For numbers between 0 and 1, it's called a vertical compression, which means it's going up slower or going down slower. So if you want to sort of maybe write that in, so if you have, if this number here, we call it a, if a is greater than 1, we say it's a vertical stretch. If a is between 0 and 1, we call it a vertical compression. All right, let's do one problem here and see if it makes sense. All right, back to the squared function here. F of x is square root of x. G of x is 2 square root of x. So can you graph maybe at least the dots for this one real quick here? And then can you stretch it out by 2? start here. Square root of x, 0, 0. Square root of 1 is 1. Let's see, square root of 4 is a 2, about right there. Square root of 9 is a 3, so about right there. There's my square root function, at least for the points to it. All right, and then this is the way I sort of think about it here, but you're stretching it away from the x-axis. 0, 0 is already on the x-axis, that does not stretch. But you have this point here, which is 1 away from the x-axis, and now what's going to happen is going to be 2 away from the x-axis. It's going to be double the amount. This one here that used to be 2 away from the x-axis, now it's going to be 4 away from the x-axis. Okay, and this one 3, now it's going to be 6, and then you can kind of see what the graph's going to look like here. All right, another way to see it, I think a little easier way to see it, is you go from the vertex or the main point here, from individual functions here. If you go 1 out to the right and you go 1 up originally, notice you go 1 to the right and 1 up. Here you're going to go 1 to the right, now you're going to go 2 up. So just kind of, each time you go away from it, you're going to double whatever you went up from. So here you go 4 to the right. In order to go 2 up, double that. Now you're going to go 4 to the right and 4 up. If you go 9 to the right and 3 up, now you're going to go 9 to the right and 6 up this time. It's a little easier to sort of see it, especially when we do parabolas. Okay. All right, here's what we're talking about here. I know I mentioned it before here. So a vertical stretch away from the x-axis is whenever a is greater than 1. A vertical compression, which means towards the x-axis, happens when a is between 0 and 1, and a is just the multiplier in front of the function itself. All right, something you guys will see quite a bit later on in math courses here. This is kind of like what's happening with the vertical stretch. We'll figure out our zeros, where our zeros are. And because we know a vertical stretch, instead of that black line being the original line, what happens is you should sort of see this here. The waves are sort of much more bigger, but they still cross at 0, 0. Good. So either is going to go a lot higher than the original graph, a lot lower than the original graph crossing. That's your x intercepts here. Okay, how about if it's a vertical compression? Notice the lines are now lower. It doesn't come up as high. All right, and the fun begins here. This one I don't think you've seen in algebra. Those I think you've seen at least maybe sometimes in algebra here. So now we go on to horizontal. What happens if you go horizontally stretch or horizontal compression? It's this little b value. It's the one that's actually multiplying your variable. So kind of say, hey, what's my multiplier on my variable? And if there is one, you got yourself a horizontal stretch or compression. This one, it works opposite of what we would normally think. Just like, remember how in the horizontal shifts, it was always the opposite way, right? If it's x minus 1, you move off to the right. X plus 2 moves off to the left. This one, same thing here. A horizontal stretch actually means it's the b values between 0 and 1. But a horizontal compression happens when b is actually greater than 1. So the exact opposite of the vertical stretching and compression. All right, what does that look like? Just as a graph here. So the blue line is the original line right here. And if we have f of 2x, so there's a multiplier of 2 on your variable, so notice what happens, everything gets stretched, everything gets compressed along the y-axis here. Everything gets compressed back to the y-axis if you think about it. That's for something having a 1/2 in front of it. the function itself is 2x. This function is 1/2 over here, and now what's happening is it's going out twice as much. Right? The x and the 2x is just a relationship between the x values here. So let's take a look at an example here. I think it'll help. All right, let's go for it here. Again, don't write it down. Just an example, just to sort of to see here. Main points are -2, -1, 0, 0, obviously, 1, 3, and then we got ourselves a 2, 0 right over here. So now that's just my original function. This is just f of x. So what happens if you put a 1/2 into here? What do you guys say? Stretching it out or pulling it in? It's only 1/2. It means it's going to stretch it out. Right. And so what we do here is we really manipulate the x-axis right here, or the x values here. So -2 now is going to go out all the way to -4. 0, 0 is along the y-axis already. It's going to stay. The x-coordinate is going to double, so it's going to be 2, 3. And this 2, 0 now becomes 4, 0. Good. So everything is moving, in a sense we say, is half as fast. That connection there. All right, the next one, 2x. Now everything gets compressed. So that 2, -1 originally here now becomes -1, -1. 0, 0 still stays. And again, 1, 3 now becomes 1/2, 3. 2, 0 now becomes 1, 0. So everything gets pulled in by that amount. All right, and then what happens? You have a negative inside there and a vertical compression. I'm sorry, horizontal compression. You got a reflection about the y-axis. Notice, bless you. This was at 1, 3. It jumped to this side being -1, 3, and then it got compressed to the y-axis. This is where things get kind of scary. Let's try our hand at this problem here. So practice problem number 7. You have this graph right here. Hey, doesn't this look like a piecewise function? Is that right? You got a linear function from -2 to 0. Then you got a parabola from 0 to 2. Okay, so some easy ones here. Can you graph for me? I won't show you the answers here for a little while. Can you graph for me f of 1/2 x? And then also f of 2x. I'll give you guys maybe a minute or so just to try it. All right, I'm going to start it here real quick here. So f of 1/2. What's that going to happen? Let me draw it on maybe a different graph here real quick here. We'll start. So original graph goes like this. Everybody agreed there? And what we're going to do is we're going to take 1/2 x, because it's between 0 and 1, you get yourself a horizontal stretch. Is that right? And so again, this -2, 0 is going to come out twice as much here to compensate for that 1/2. Anything along the y-axis is still going to stay because there's no changing along the y-axis, so that's an easy one to sort of see. There's my stretching from -2, 0 to -4, 0. 1, 1 will have to stretch as well. Now again to 2, 1. And again 2, 3 looks like is going to stretch twice away from the y-axis, so how about 4, 3? Good there, and then we put it all together. There it is. So f of 1/2 x all right. As far as sort of thinking about it here, in my mind here, what I always think about this, if this was just a regular x and I put a 1 into there, I'm evaluating this function at 1, right? Now because this 1/2 there, in order for me to get to 1, I actually need to have a 2 in for the x value. We're good? Does that make sense? So if I get a 2 in the x value, half of 2 is 1, so now I'm finally evaluating 1. Okay, so notice the stretch that happens there. It's like you sort of think, okay, what do I put in order to get back to evaluating that specific number? That's the way I think about it here. Okay. Next one, b. F of 2x. Again, original function goes like this. (2x) in order to evaluate 1, or f of 1, I'd have to be at 1/2 in order to do the same thing. So now that we got ourselves a compression. So again, -2, 0 now becomes -1, 0. It's scooting in halfway. 0, 3 is going to stay 0, 3. 1, 1. How about we scoot this back all the way back to 1/2? So this gets stretched back to 1/2, 0 instead of 1, 0. And then 2, 3, that's going to go halfway back as well. So how about just 1, 3? And my graph sort of looks like this now. All right, we good there. We're making it through slowly. I encourage you guys to read ahead, at least look at it, at least scan the section, at least you know what we're going to talk about. Maybe if you have some extra time, try some practice problems, at least the first 1 or 2 or 3 or 4. That'll get your mind at least at ease at what you're going to look at or what you're going to be seeing. All right, well, just like order of operations, we have transformations. They do go in order as well. So we go with, first thing that you look at, usually look at the horizontal shift. Second is any stretch or compressions that we have. Third is reflections, and then you got your vertical shift, the last one here. If you do get them mixed up, yeah, then it's all get jumbled up here. So this is the correct way on page 249 even. Let's see, on page 249, it talks about a practice problem number 8, and they show what happens if you do it the incorrect sequence. And if you do that, then things get jumbled up. So there's a correct sequence to looking at these things here. So let's go for it here. Let me give you an example first, and then we'll jump to practice problem number 8. So example, here it is. We're going to graph this little guy, -2x minus 1 squared plus 3. First thing is we're going to focus on, this little middle section right here, x minus 1. We're going to say, hey, you know what? This graph is actually going to shift over to the right 1 unit. There's my step 1. I've shifted over. My vertex is no longer at 0, 0. Now it's at 1, 0. Cool. The next step is any vertical stretches or horizontal stretches or compressions. So in this case, just thinking about this little 2, forget the little negative on the outside. Just think of this here. That 2 means this thing is going to go up twice as fast. So instead of it being, now this one's not going to move, right? But instead of it going 1 to the right, 1 up, now it's going to go 1 to the right, and now it's going to go 2 up. That's what I meant by a vertical stretch. You always start off where you are along the x-axis, and you move out left and right. All right, so there it is. You go 1 to the right, 1, 2 up now. There's my vertical stretch. Any reflections? Yes. Now we turn the whole thing around. So this whole thing, instead of going up away from the x-axis, now is going to go down away from the x-axis. And then any vertical shifting that we need to do. Yes, the original function had a little +3, I believe. And so that little 1, 0 now gets shifted up to here, and there's our final function. Whew. Now, when you plug this into the calculator, what does the calculator do? it just calculates, because it can do that real quick. It calculates 2.73640, plots it. Then it calculates 2.87635, plots it. 2.9735, plots it. 3.003, plots it, right? Just kind of uses random numbers across, puts individual points. It would take us a year if we did that. Okay, so that's why we have to use transformations. All right, our function, looks like today we favor the square root function here, so go for it. Square root function. You know what the square root looks like? Think about the little +1 that's on the inside of it. Then give your attention to the 3 on the outside as a multiplier, and then the -2 as a subtraction. All right, to give you guys a minute or so, maybe half a minute here. Try it yourself. All right, I'm going to start it as well here. So the square root function, again, only putting dots, because I'm going to do a whole bunch of graphs here, but 0, 0, 1, 1. Square root of 4 is 2. Square root of 9 is 3. There's my original function. That's what I start off with. And now my question is, any horizontal shifts? Absolutely. X plus 1 means I'm going to shift over to the left 1 unit. So in this case, let me do it here. All right, so everybody okay with this little plot right here now, right? Good there. This shifting over, and this one shifting over. Good there? Okay, from here, I'm getting too confused here now on things here. Let me see maybe how I can change this to a different, there it is, okay. Horizontal shift taken care of, right? Next step is any stretches or compressions, both vertical or horizontal. Yeah, I got myself a vertical shift, vertical stretch. So anything that's on the x-axis stays, but then this part right here, because it's only 1 unit away, I got myself a vertical shift of 3, therefore I'm going to have, instead of 0, 1, how about 0, 3 this time? So again, this one stays as is. This one is now up here. Let's see the next one here. This is 2 away. Now it's going to be 6 away. We're good there. This one here, 1, 2, 3. Now this is going to be 9 away. So there's my vertical stretching. All right, one more. Maybe I should graph on this one here as the last one here. Then from here, then I have this little -2 at the end. Right? So I've taken care of the 3 in front. I've taken care of the +1 over here. Now let me take care of the little -2 in the back. I didn't have to do any reflections, so no number 3 that I had to do. Number 4 is vertical shifting. Yep, and I gotta shift this guy down 2 units then. So my new point is right here. So let's see, that's gonna be 1, -2. This one's gonna go down again 2 units, 1, 2. We're gonna go back down to 0, 1. All right, this one, again, down 2 units, 1, 2. So now my final answer is going to be a 3, 4. And this one, 1, 2 units down. So how about 8, 7 now? And there it is, final graph. Again, still a square root function. Again, but manipulated a bit. are we good there? Got pencils almost down. Got a few people still writing it out. Kind of dry stuff, you know, just graphing functions, that's it. Fun when you start building stuff with it though. Like, oh, that's why, because of the hardness of the cement and this and that, that's why we have to shift it over to this, or that's why we have to construct this building this way. Because, and then you have to use then you got calculus here, because then like, okay, because the center of gravity is going to shift this way, then you're kind of calculating everything all at once. That's when things become fun. Okay, I think we're good there. All right, so let's go for it here. A sequence of functions. Let me show you an example here of something, then we'll just try our last problem here for this section. We have this function, and here's the graph of it right here. It's already given to us here. It's a graph that looks like it's a constant function up until 2, and then maybe sort of like a, I don't know, a linear function this way maybe, and a linear function that way. So a piecewise function, and then let's kind of run through here the steps on it here. So notice you got this little +4. A few remarks here I guess we should make. You could either write it like this, or you can write it like this. True? Is that the same thing? So you could either have it like that. Some textbooks, they even actually do this here. They actually even factor out the multiplier. They'll factor this out, and it becomes x minus 2. Everybody okay there as well? Okay, all those based upon that is still going to give you the same exact graph at the end. So even though these are exactly the same, but if you take a reflection horizontal stretch by 2 and you take 2 out, you're still going to wind up with the same exact spot. So anyways, let's run through one here real quick here. So that little +4 right over here, what that's going to do, it's going to shift it over to the left 4 units, is that right? Technically have yourself a little +4 inside the function. So we're going to take this 4, 0, we're going to shift everything back. 2, 3, now it becomes -2, 3. So notice the new graph here is shifted back 4 units. And then we just keep on going. What's the next step? We got to do any stretching, right? Or compressions, right? Stretching or compression. So let's see. So because that little 2 there, no, it's a +2 at this point. All right, here's the one from the previous slide. And then what we're going to do is we're going to compress it, because that little 2 being there, you got a compression. Now you're going to go, everything's sucked into the y-axis. You got yourself that 1/3 on the outside. Because that 1/3 is there, now you got yourself a compression again, is that right? Now it's only going up to -1, 1. So it's compressed from -1, 3. Say again? Remember, because inside that's a horizontal compression, and if it's higher than 1, it's actually a compression. If it's between 1 and 0, it's a stretch. The vertical stuff works exactly opposite here. If it's a 1/3 or between 1 and 0, it's a compression. If it's higher than 1, it's a stretch. So -1, 3 now becomes -1, 1. 1, 6 got back down by a factor of 3, so now you're only going up to 1, 2. So we have compressed it vertically. Now we look at our reflections here. So there's a -2 instead of a +2 in front. So we're going to take this guy, reflect it across the y-axis. Is there a reflection about the x-axis? I think so, because of a little negative right here, right? That -1 there. So we compensated already for this little negative here now. That's cool. Now let's compensate for this little negative here. And so all we do is we just bring this reflected across the x-axis. We're almost there. Got the negative 1/3 now. I got the 4 minus 2x, and I still need this little plus 5. So that 5 is now going to bring everything up 5 units. Our final graph looks something like this. Oof. A lot of stuff to keep in your head. I know that's pretty tough there. Sort of go in sequence here. On page 248, I think the best way to, if I were to give you a hint here, page 248 is a good one. On top, it kind of just tells you what's your sequence. Number 1, you got your horizontal shift, right? Number 2, your stretch or compressions. Number 3 is all your reflections. And number 4 is your vertical stretch. If you sort of keep that in sequence, keep on going through that sequence, that's going to be a lot easier to sort of think through. All right, let's do a somewhat easy one here, just for us to try. Practice problem number 9, and the last one here. So use the graph of this guy here to obtain 1/2 f of 2x minus 1 plus 3. All right, let's go for it here. Again, if you have the textbook in front of you, you want to just copy it out, that's fine too. All right, use the graph, this guy here, to graph now this one. So 1/2 2x. So first thing I'm going to worry about is this little minus 1 right here. All right, that minus 1 does what? Moves everything to the right. 1 unit, okay, so let's kind of put in some dots here if we can here. So everything gets moved over to the right. So I got this guy here, boom. Negative 3 4 now becomes negative 2 4, got that one. This becomes 0 0 here on our hands now. And this becomes 4 negative 2. Again, just putting in dots so at least I know where that's at. That's horizontal shift, right? Next is any stretching. Or compression. Right? So let's go horizontal first, because once we so got that little 2 here. What are we going to do here? So there's my horizontal shift. This guy's going to be a horizontal compression, right? Much here. So let's see, 0 0 stays, no change here. Let's see, this guy here, which is negative 2 4, now becomes, let me change color here so I can see it as well here. All right, how about go back to red here? So let's see, it goes to here now. So now this guy, I'm going to label it here. This will be negative 1 4. This was negative 4 0 right here. So now it's going to be negative 2 0, which is right here. Negative 2 comma 0. All right, let's see. This guy was 4 negative 2. Goes back over here. Bless you. And now it's 2 negative 2. Okay, good there. If we want to draw it, that's fine. Just kind of want to be able to sort of see where I'm at here. I got myself this now. So, all right, 1/2 here. I've got to do that one still. That means, let's see, everything is going to be compressed by 2, right? Okay, cool. So then all the stuff that are all on the x-axis, that stays. There's no change here. So this guy here, negative 2 0 still stays, no change. 0 0 still stays, no change. So negative 1 4. This dot here now became negative 1 2, and this dot here that was at 2 -2 now became 2, -1, so down to here. Okay, are we good there? Almost done. Then we got to do this little +3 here. +3 means we're going to shift everything up 3 units. And so let me do that. So this guy here, 1, 2, 3. My last dot is here. Let's see, this guy -1, 2. 1, 2, 3. Now it becomes, I guess we should label these, right? -2, 3. Label this guy here. This could be -1, 5. The 0, 0 now it becomes 0, 3. And 2, -1 now becomes 2, 2. And so there it is, final graph here. I got this, and I got this as my final graph. All right, good. Where do we look at it in calculus? You should be able to look at a function and say, oh, this is x minus 2 squared. Okay, now I know where the graph is. Or at least now I know where the x-axis is, the x-intercepts. So you should have a good idea of where things are sliding. All right, so that is the end of 2.7.